Okay, so we left off talking about how do we turn English into a chemical equation. So when a solution of lead-2 nitrate is combined with a solution of sodium carbonate, a precipitate forms. Write a chemical equation to represent this reaction and indicate the states of the products. So you'll notice I italicized a couple words, and I did that because I wanted to emphasize that they can be used to help you think about what kind of reaction is going to be occurring, and they help us write down the reaction. So if I have a solution of lead-2 nitrate, then I have lead-2 nitrate that's aqueous, and I have aqueous sodium bicarbonate as well. And then it's telling me a precipitate forms. So I can identify this as a double replacement reaction. So my plan is I'm going to write the formulas for the reactants first, just to make sure I can get that taken care of correctly. So lead-2 nitrate, nitrate is 1-, so I'm going to need 2 nitrates. It's aqueous, so I'm going to put the little AQ down here. And then we have sodium carbonate. Sodium's charge is 1, carbonate's charge is -2, so we need 2 sodiums, and that's also aqueous. So we've used a lot of our information that this gave us. The next thing we want to do is do the swap. So we've identified it as a double replacement because it's 2 ionic compounds in solution. So we're going to swap the cations and balance the charges. And if we do that, that gives us sodium nitrate. Sodium's 1+, nitrate's 1+, so that's good. And then lead carbonate. Lead is 2+, carbonate's 2-. Perfect. So our charges are balanced. Now we can move on to step 3. So for step 3, we need to predict if the products will be solid, liquid, gas, or aqueous. We know that one of them is solid because it tells us a precipitate form. So we just have to figure out which one. And to do this, we can use Nonacol-Noso and Pabagokapos. Remember, these lists are on your cheat sheet, so you'll always have them. So the first product, NaNO3, sodium nitrate, those are both Nonacol-Nosos, which means they are very soluble. So I can say right off the bat, sodium nitrate is going to be aqueous. The other one I have, lead carbonate, both of those are in Pabagokapos, which are my unsoluble, I guess it's insoluble, ions. So I can confidently say, because of Pabagokapos, that lead carbonate will not dissolve. It will not be aqueous. It will be a precipitate. So that allows me to add my little subscripts that talk about the state of matter. So sodium nitrate is aqueous, lead carbonate is solid. Now that we know how to write and depict our reactants and our products, we can put it all together. So we'll write out our full equation. We have lead nitrate plus sodium carbonate that's aqueous, and that gives us aqueous sodium nitrate and solid lead carbonate. There it is. Okay, so we changed our equation from English into chemistry speak, and by chemistry speak I mean formulas. But we're actually not quite done because we do not have the same amount of stuff on both sides of this equation, which means we've violated a fundamental law of physics. Whoops. So we violated the law of conservation of mass, which is saying that mass can't be created or destroyed. It can just change forms. So if I take a little tally of my reactant side, what I have going into this, I have 1 lead, 2 nitrates, 2 sodiums, 1 carbon, and 9 oxygens. Okay, so This 2 distributes on everything in parentheses, so it's 2 nitrogens, and 3 times 2 is 6, plus these 3 oxygens gives us 9 oxygens. On the other side, we have 1 lead, so that's okay. We have 1 nitrogen, that doesn't match up. We have 1 sodium, that doesn't match up. We have 1 carbon, that's okay. And we have 6 oxygens, so that's not good. Like, we lost 5 atoms somewhere during this reaction, and that's just not a thing that happens. We have observed it hundreds of times. The atoms never just disappear. They can always be accounted for somehow. And because of that, we have to kind of incorporate one last step to writing our chemical equations. So just a formal definition that is not in a meme is that the law of conservation of mass says that mass is neither created or destroyed in a chemical reaction. This is my definition for you that's applying this really explicitly to chemistry. This applies in other situations as well, and we'll have probably a more, I don't know, broad, sciencey sounding explanation, but for our purposes, we just need to know you can't get more stuff out than you put in, and you shouldn't get less stuff out than what you put in. Okay. Yeah, that's not how it works. So because of that, we have to balance our chemical equations. So to talk about balancing chemical equations, we are really just trying to account for the different elements on both sides. Like, if I put a carbon into the reaction, I have to get a carbon out of the reaction. If I put 2 sodiums in, I have to get 2 sodiums out. And I picked this really pretty picture because I was looking for a picture of a teeter-totter, you know, because balancing, right? And then I was like, ooh, I want to look for dogs on teeter-totters because I like dogs. So I Googled that, and then this popped up, and I have no idea what this is about. Raphael the raccoon and Donald the dog and Kit the cat just out there living on their seesaw, I guess. But honestly, I'm sure that looking at the context would completely spoil it. I don't know. I just think that raccoon is so funny. Why is he playing with a dog? Like, that's just foolish. Anyway, so here's our chemical equation that we wrote out, and we need to balance it. So the first thing that I do if I want to balance an equation is count the number of each element on the product side and the reactant side of the equation. So I just make myself a little table because I'm type A like that, and I count them up. So we did this before, and we could see that we have on the reactant side on the left 1 lead, 2 nitrate, 2 sodium, 1 carbon, and 9 oxygen. And then on the right in the products we have 1 lead, 1 nitrogen, 1 sodium, 1 carbon, and 6 oxygens. So like, obviously that doesn't add up. Like, we just lost 3 oxygen atoms. How irresponsible. So we have to come up with a way for us to account for that. So the second thing we do is identify the elements that occur in different amounts on both sides. So I highlighted them in yellow for you. So we need to address the fact that we didn't get enough nitrogen out, we didn't get enough sodium out, and we didn't get all of our oxygens back out. So the next thing I like to do is find the elements in the equation. So now I've given them each their own color because I love pretty colors, you guys know that. So I found my nitrate. So my nitrate is only occurring, my nitrogen is only occurring in 2 spots. It's with the nitrate, so that's good. And then my sodium is occurring in 1 spot on the reactant side and 1 spot on the product side. And then my oxygens are occurring in 4 spots. So that's a lot of oxygens to keep track of. So I've highlighted those green. Now we need to think about what coefficients. So the coefficients go on the lines and they multiply the whole compound. So they would say you have 2 lead nitrates or you have 2 sodium carbonates, right? They're just telling you of multiple of the molecule. So what can we put in front of the compounds to try to balance the elements? And we're going to first add coefficients to the side that has fewer elements because we're trying to balance it out. So we don't want to add coefficients to the side that already has too many. So when I'm looking at this, I'm like, okay, I definitely need to add to the product side. And since I'm like multiplying, because I am just like adding another molecule, so I'd be doubling the number of molecules, or I could multiply by 3 and triple the number of molecules. I wish you guys could see me gesturing by myself in my office. It looks ridiculous. Anyway, so I think what I want to do is I want to put a 2 in front of my sodium nitrate on the right-hand side, because then I would have 2 sodiums, 2 nitrogens, and 6 oxygens on that right-hand side. Okay, so if we put a 2, go away, little bar. We put 2 in front of sodium nitrate, that will make it so that there are 2 nitrogens, 2 sodiums on each side. And I'm really mostly concerned with those 2 right now. We always leave oxygen for last because it's a pain in the butt and it's annoying because it's like everywhere all the time. So we just kind of ignore it until the end, which is how you should address all your problems, honestly. That was bad advice, don't do that. Number 5, step 5, count all the elements again. So the reacted side is unchanged. So I rewrote them, but you know that they're the same number, right? We didn't multiply any of those guys. On the product side, we went ahead and we doubled our nitrogens, we doubled our sodiums, and we doubled these oxygens, so we got 6 now, plus those 3 is 9. Okay, so we updated our counting, and now we're like, hey, 1 lead, 2 nitrogens, 2 sodiums, except that I didn't write an A next to it, so it only says in. Just pretend there's an A next to it. And then 9 oxygens and 1 carbon. So we're like, dude, this looks great. And fixing the other elements, the sodium and the nitrogen, also happened to fix our oxygen, which is pretty slick. So I feel good about that. Yeah. All right. So at that point, you're really done. However, if one or more elements is still unbalanced, you might need to add another coefficient or change a coefficient. So you really need to repeat steps 2 through 5 until all elements are equal on both sides. So you need to keep counting them and then seeing where the mismatch is and trying to change coefficients. And we're going to do some examples like that. So you're also going to have a PhET practice where it lets you like see the number of molecules and stuff, which I think is so helpful to for visualization. Yeah, so that is oh no, it's not, just kidding. So couple just side notes, you can fill the other blanks with 1s. So you could say 1 lead nitrate, 1 sodium carbonate, 2 sodium nitrates plus 1 lead carbonate. I usually just leave them blank. Do whatever feels good to you. If you want to write a 1 in front, great. If you want to leave it blank, great. It's like implied that there's a 1 if you leave it blank. Second thing is always balance hydrogen and oxygen last. Hydrogen also tends to be kind of a pain in the butt to balance. So we want to try to get the other elements all sorted out first, and then we can address the hydrogen and oxygen last. And do oxygen very last of all, because it's the most annoying. Okay, that concludes part 2. There will be a part 3. Sorry, this is so long. sometimes it just be like that.